No. Hello and welcome back to Calculus 1. This is exam 2 review on chapter 3. So we already discussed the list and some quick problems. Hopefully you have more problems to take a look at. So chapter 3, 10 problems. We have the ways to take the derivative in chapter 3, 11 sections, right? So we have the limit definition of the derivative, which is a statement, and the way to do it, which is 2.3 calculation actually. Then we have taking basic derivatives, which is constants, polynomials, rational radicals, ln, e to the x, trig, and all of that good stuff. Product, quotient, chain rules, implicit differentiation, logarithmic differentiation, related rates, word problems. I said probably two problems, one that is very easy and one that is kind of medium spice. And then possibly rates of change, which is also the word problem, where you look into the derivative of path to get velocity, derivative of velocity to get acceleration, set velocity equal to 0 to find time, and plug that time back in original path function to find maximum height, and stuff like that. But we also had that word problem with the cost function, so that we can calculate marginal cost. That's also good stuff, and so on. And then we just looked at some random problems where I worked out some of the more interesting and some basic cases in terms of related rates. There was also a nice, oh yeah, let's not forget there was a suggestion to also include the definition of the tangent line, which is good. And then also this type of a problem where we get to solve the same problem in three different ways. So we solve the quotient rule using the quotient rule, then the product with the chain, and then eventually logarithmic differentiation, obtaining the same answer every time. So that was what happened yesterday. It was a brief review, but it contained a lot of stuff, as you can see. So let's see, what is for today? What do you guys have as problems? Yes?
One question. Will you be posting all the notes?
Yes.
For the review today?
Anything, any questions, any problems? Yes?
Will you follow the LN or not?
Yeah, which one? Then we can't. Yes.
We do like a tangent inverse form.
Which one?
2 tangent of inverse e to the 9x.
What are you supposed to do with this? Cook it?
Find the derivative.
Oh, find the derivative. Okay, fine. See? That would be like me walking up to you and saying 17 and just walk away. And you go like, 17 what? 9x. This is clear. This is a 9. It's spelled out. I know. So we copied the constant, which is 2. And then we have the derivative of the tangent. The derivative of the tangent, if we put the basic tangent inverse, if you study it at all, it's 1 over 1 plus x squared. The better version, oops, supposed to put the derivative in front. The better version would be the derivative of f of x, which is exactly what we have here. And that would be f prime of x divided by 1 plus original function squared. So I have to put the derivative of 9x on top, which is 9. No, hold on. Let's first deal with the denominator. 1 plus, this is f of x. So we need to square that. That's going to be e to the 18x. And now take the derivative of e to the 9x. That's 9e to the 9x. There we go. And now to simplify everything, this is going to be 18e to the 9x divided by 1 plus e to the 18x. Ta-da! Happy? Good. Any other questions, concerns? Yes.
Can I do a word problem?
I hope I can.
It says a piston is seated at the top of a cylindrical chamber with a radius of 3 centimeters. It's when it starts moving into the chamber at a constant speed of 6 centimeters per second. What is the rate of change in the volume of the cylinder when the piston is 8 centimeters from the base of the chamber?
So rate of change of volume. What did you say was the last part?
When the piston is 8 centimeters from the base.
Nice. So we have a cylindrical chamber, which I'm going to just give the cross section this way. And then we have, so this is actually round, right? It's round. And then I have a cylindrical piston that fits in. This is how the engine works in the car. And this cylindrical piston will be going up and down. So the radius is 3 centimeters. And we know that this height over here is 8 centimeters. And we have the velocity of the, which is the change, right, of distance. So velocity here, I'll call it, let's call this distance h, right, for height. So the velocity is actually dh dt because it's changing the height. So when your distance could be height, right? Heights are distances. So when you're changing any kind of a distance, including that height, that's going to be a velocity, and that's what's given to us. So at the speed, the piston is moving at the speed 6 centimeters per second. So now we have understanding of this, and we can finally do things. They want a rate of change of volume. So d capital V dt is the question mark. Now for cylinder, we know that the volume is base times the height, and the base is pi r squared times the height. Now radius, I said squared and I put cube. There we go. And we know that the radius is 3 and it's a cylinder, so that's fixed. So the volume in this case is going to be 9 pi h. And when I hit this with a time derivative, we are going to have dv dt is equal to 9 pi dh dt. So dh dt is given as a velocity which is given as 6. So dv dt is equal to 9 pi times 6 for the answer of 54 pi centimeters cubed per second. Yep. Centimeter cube per second. So What they're looking for is dV dt, and I have it as a 54 pi, so it's about 160, 170, whatever it is, centimeter cube per second. Now, I'm really puzzled why they gave us 8 centimeters from the base. That was completely, I haven't used it anywhere. Maybe to throw me off, but as you can see, the cylinder is there. We have the velocity. The volume of the cylinder has a linear height. When you take the derivative of that height, it becomes dh dt, so there is no, like if it was h squared, then you would have 2h dh dt, and then you need h to plug in. But in our case, I'm really not sure why they put this in.
Is the radius?
No, it's cylinder.
I mean, for the sake of the problem, I could expand, right?
Nah, they didn't put any of that stuff.
That's the only instance.
Yeah, but we don't have the rest of the stuff for expansion then. The radius is constant, they said, at 3 centimeters. So, yeah, you would have to worry about that for the design of the engine, because clearly 1,000 degrees, right, will expand slightly. So you have to count for that when you are designing an engine block. But in this case, they didn't say anything. They just said radius is 3 centimeters. Velocity of the piston, which is dh dt actually, is going to be 6. So that's that. There's no gravity involved. There's, I don't know. Interesting. All right, anything else? That will be it. Any other problems?
I give you a problem.
I'm waiting. I asked for a problem, and now I'm playing on my phone because no one is saying anything. I was literally ready to play for another hour and a half and just leave, walk out without even saying goodbye. So, yeah. Feel free to talk to me at any point, but, you know. You can always roll back the stream when I did ask, like twice, so fine. Sure, what's the problem?
Find the derivative of f of x equals log base 5 2x plus 1.
All right, great. Well, thank you. That makes, right? So, what happened?
Didn't she say 2x plus 1?
Yeah, 2x.
She did. Okay, good. Thank you, she. All right. So, the derivative of all log functions are always the argument as is in the denominator and its derivative on top. So that's always the case when you have ln. Now, since you don't have ln, you have log base 5, you will have to multiply in denominator by ln. So ln of some f of x is going to be f of x as is in denominator and its derivative on top. If you have the derivative of other base than e, which means log base a, whatever that a is, of f of x, so that f of x could be trig, could be whatever else, it's also going to be f prime of x divided by f of x, so the same thing, except now in denominator we also have ln a. So these are the two formulas that, I mean, obviously the one on the bottom is the general formula for everything, which would include ln, because ln is just a special base when a is e. But as I said, 99% of the time, use this, right? That's the problem that you are running into. Great. Are there any other problems? This is where the cooldown starts in my head. 10, 9, 8, right before I go there. Yes.
Take the derivative of x to the fourth over x squared minus 3 to the fifth.
Like this?
Yeah.
Oops. Nice. I can't put my brackets. There we go. That's square. So, I will use logarithmic differentiation, and instead of just writing the answer, which I can obviously, I'm just going to work out all of the steps so you can see those steps one more time. Y is equal to x to the fourth, we leave some space, x squared minus 3 to the fifth, and then we put in ln on both sides. Now, left-hand side is ln y, right-hand side needs expanding. So it's going to be 4 ln x, because the exponent 4 goes in front of ln, minus 5 ln of x squared minus 3. Now, x squared minus 3 cannot break through ln formulas unless you factor it and get x minus root 3, x plus root 3, and then you can. But it's just overkill, so no reason. Once you expand everything, we differentiate implicitly in terms of x. On the left-hand side, we have 1 over y dy dx is equal to, on the right-hand side, we have 4 over x minus 5. Denominator is x squared minus 3, and the numerator is 2x. Y will go to the right-hand side, so I just have dy dx. And on this side, the y is x to the fourth over x squared minus 3 to the fifth times 4 over x minus 10x over x squared minus 3. As you can see, this derivative is already factored, ready to be equal to 0 to find the values. When you equal the second parenthesis to 0, you will do cross multiplying, right? You make first 4x equal to 10x. And then you cross multiply, you solve quadratic equation, and so on. So yeah, one of the answers is 0, which you have to throw away because you have the vertical asymptote there, and so on. But, you know, there are things in chapter 4 that you will enjoy once you reach that. Any other questions, concerns, anything? I'm sorry? Over here? Oh yeah, you can use quotient rule with the chain, sure. You can use quotient rule with the chain, but that will be just a lot of work. Logarithmic differentiation supposed to save the, and you know, all that work. Any other questions? 9, 8, 7, 6.
Marginal and average cost.
Okay, so average cost is when we take the cost function and divide it by the number of units we are producing, and the marginal cost is the derivative of the cost function. What's the example? The average cost, I just gave the definitions that I wrote in class. So the average cost is when you have a cost function and you divide by the number of units produced. So average cost is the cost function divided by the number of units produced, and the marginal cost is simply the derivative of cost function. Now that definition was given to you in rates of change, I believe 3.5 or 3.6, whatever it is. Maybe 3.6. Good. So those definitions are in there. Yes.
2x plus 2y equals sine y, and the derivative
2x plus, hold on, 2x plus
2y
okay,
equals sine y of the derivative e squared to the y dx squared.
Is this what you said?
Yeah.
Oh. Find the second derivative, yeah. Whew, it is going to be spicy. Why is it going to be spicy? Because it's implicit differentiation, they're asking for the second derivative. All right? Start a new notebook. Let's go. We first have to find the first derivative in respect to x. And that would be simply x plus, 2 plus 2 dy dx is equal to cosine y dy dx. So we take derivatives term-wise. We do not have any product rule, chain rule, quotient rule, or any of those things. We do have the chain rules for dy dx every time we take the derivative of y, but other than that, we just plow through. So now we have that 2 is equal to cosine y minus 2, and we factor dy dx, right? So we move the term to the right, and then we factor out dy dx, so that's cosine y minus 2. And then you divide that term into it. So what's dy dx? Dy dx is 2 divided by cosine y minus 2. So that's our first derivative. Now we take the derivative to get to the second derivative. Now observe the notation. When I put another d dx in front, then d times d becomes d squared from our times single y, divided by dx times dx is dx squared. So that's why the notation is d squared y over dx squared, right? D times d is d squared, and then dx times dx is dx squared. On the other side, we could... Here we go. I want to see that breakfast at work. You tell me, yeah, I had 2 eggs. No, 6.
6 eggs?
Yeah. See that door? I walked to the closed. 6 eggs, bacon, tomatoes. I had sleeves now. I don't. See you tomorrow, walk through the wall. You make sure tomorrow you walk in, it's test tomorrow, right? So, yeah, no closed doors will keep you from, right, getting in. And then when they ask you what happened to the wall, there was an exam, and professor said even if we're dead, we have to wall in somehow. So, yeah. All right, back to the problems. Now I have to go again. So, we have the first line there. We're supposed to find the second derivative. We find the first derivative first. It is the implicit differentiation. We go term by term. Derivative of 2x is 2. Derivative of 2y is 2, and then dy dx. And then derivative of sine y is cosine y. Then we, apply some algebra here and there. And we get to the statement there that the first derivative is equal to 2 over cosine y minus 2. So now, when we are at that point, we find the second derivative. So we hit the first derivative with another derivative. D times d is d squared. Dx times dx is dx squared. So that's the second derivative. On the other side, you have a choice of doing the, hopefully not, quotient rule, or, much better choice, chain rule. Because this could be written as 2 times cosine y minus 2 to the negative first power. So now if I am taking the derivative, I copy the 2. Then I take negative 1 down, copy the guts, right? So that's cosine y minus 2 to the negative 2 times the derivative of the inside, which is derivative of cosine is negative sine y. And then I have to follow with dy dx because I took the derivative of y. So yeah, it's a little bit convoluted, but it's the solution, right? So if I write that problem as chain rule, then I don't have to worry about quotient rule doing it forever. So now I just have to put all of these minus signs together and all of the stuff. So let's do even more algebra now. I have negative 1 and the negative over here will cancel. And all I have in the numerator is going to be 2 sine y. Denominator is going to have cosine y minus 2 squared. That negative 2 exponent pushes everything downstairs, right, with the positive exponent. And I still have dy dx. Now, I know what the dy dx is. So plug it in, all right? So plug in 2 over cosine y minus 2, because that's what the first derivative was. So we can have everything in terms of just x's and y's rather than having in terms of x's, y's, and first derivative as well. So now I have 2 sine y divided by cosine y minus 2 squared times 2 over another cosine y minus 2. So the final answer over here would be 4 sine y of cosine y minus 2 cubed. And that would be it. That's the final answer. Nice. Nice question. Are there any other questions that you might be interested in? 9, 8, 7, 6, 5, 4, 3. Yes.
13 to the negative x sine x is the derivative.
So derivative of 13
to the negative x. and then sine x.
Here or in the exponent? Beautiful question. You're giving me some very good ideas for tomorrow. Everyone's like, and he's like, oh, there go my tires. So we have a product rule because here's a function number 1 and the function number 2, right? And they're multiplied. So we copy the first one, which is 13 to the negative x, and then times the derivative of the second one, which is cosine x, plus copy the second one, which is sine x, times the derivative of the first. Now that's the exponential one. We have to start with 13 to the negative x times the derivative of the exponent, which is negative 1, times the ln of the base, which is ln 13. So what I have is now 13 to the negative x cosine x minus 13 to the negative x sine x ln 13. I can factor out 13 to the negative x and in parentheses have cosine x minus sine x ln 13. I will just put this aside and then you guys can work it out, or you could find the derivative of sine x over 13 to the x using chain rule. Oh, sorry, using quotient rule, because that negative exponent can push it down in the denominator as a positive exponent and then just use the quotient rule. You have to get the same answer. Observe that this will go down as the denominator, right? So you are looking for the answer that will fit the same. So, you know, you either do product rule or you do, in this case, you do your quotient rule. That was a very good question. No coffee. Anything else? By all means.
F is sine x over cosine x plus 1 squared. And I'll put the value.
Plus?
Yeah, 1 squared.
1? Oh, everything squared.
1 squared, yeah.
Oh, this is screaming. What? This is screaming what? To find the derivative. What method? Anyone?
The sine x is not in the...
Oh, it's not in the exponent? Oh, so disappointing. So disappointing. Fine. They will be brilliant. There will be only one method in the galaxy that does it. But now you can just use anything now. It just killed it. What happened? I would do it like this. You'll be like, oh, magic. All right. Well, logarithmic differentiation. I mean, there is nothing else that we can really do to be efficient with this problem. And then we'll have to address your question since you are so interested in it. So we have x sine x divided by cosine x plus 1. I really need to learn how to let it go. I'm still bothered by it. See this problem tomorrow with the sine x and the exponent. Like, yeah, there we go. somewhere at home shaking. Gotta do it. Gotta love OCD and stuff. It's amazing. All right. We have ln y is equal to, now we have the product, so that's going to be ln x plus ln of sine x minus 2 ln of cosine x plus 1. And now we're going to hit this with the derivative. So, on the left-hand side, 1 over y dy dx, that's standard. On the right-hand side, we have 1 over x plus, remember, copy the function as is in denominator, put its derivative on top, minus 2. Again, copy the function as is in the denominator, put its derivative on top. Now, dy dx, y goes to the other side, and I'm just going to fill it in right away, so I'm not writing this 15,000 times. And then have 1 over x plus cotangent x plus 2 sine x over cosine x plus 1. So, it would be a good exercise for everyone to study the difference between x to the n, actually let's go this way. Let's say x cubed versus 3 to the x. This is x to the x, right? So this is a polynomial. Therefore, we are using nx to the n minus 1. The next one is the exponential. And that one will be using good old b to the x ln b, because there's a 3 there. And then the last one, is function composition. Now we really can't use the chain rule on this one. We use log differentiation to deal with it. So the question was, you will hopefully study those. The question was, what would you do if you have to find the derivative of x raised to the sine x? What do we do? Well, logarithmic differentiation to the rescue. We ln both sides, and this ln allows us to peel off sine x in front, so I have ln y is equal to sine x times ln x. So now we hit this with the derivative, and you actually have a product rule on the right hand side, but you know, such is life. So dy dx is equal to, copy the first, which is sine x, times derivative of the second, which is 1 over x, plus copy the second, which is ln x, times derivative of the first, which is cosine x. So the derivative dy dx is equal to, we have x to the sine x times sine x over x plus ln x cosine x. No coughing. And that will be the answer. Questions, concerns? What's the next question? Anyone? Before we go into 4.2 and take even more derivatives and second derivatives, which is 4.2. That's it. Going once, and twice. So, all right. We'll hit the break.